chemistry. Today we are going to discuss about most important reaction in organic chemistry. That is, when we are focusing JAM exam, we can say Favorskii rearrangement is one of the most important reaction. In every examination, you can see question from this concept, Favorskii rearrangement. So this is a series of videos. So in each video, I am discussing one of the most important name reaction. Here I am going to discuss about Favorskii rearrangement. Okay, so let's see what is Favorskii rearrangement. So in reaction, first of all, in reaction we have a substrate, and clearly you will have reagent, and finally you will have product. Okay. The most important thing regarding with this reaction, you will have a substrate that should be alpha haloketone. Okay, so this is CH3. This is called alpha haloketone. Alpha haloketone. Okay, so this is the key point to identify this name reaction. So when you have alpha haloketone along with reagent sodium hydroxide or sodium alkoxide, okay, sodium alkoxide, okay, you will end up with a rearranged product. You will end up with a rearranged product. So I am first dividing these two category. So this is NaOH, this is alkoxide, NaOR dash. So you end up with an acid, carboxylic acid. So how it is? Clearly you will end up with a carboxylic acid, OH. And beware that you should have the same number of carbon here. Okay, so how many carbons are there? 1, 2, 3. So that 3 carbons should be there. Okay, that is. Okay. So this is a rearranged product. Similar way, you will have an ester with sodium alkoxide. An ester with sodium alkoxide. That is the charm of this reaction. Why? So see, you can easily identify the product. If you have a starting material alpha haloketone, when your reagent is the well-known base sodium hydroxide, you will end up with the carboxylic acid. Okay. So this is acid, carboxylic acid. This is ester. The thing is that how many number of carbon is there in your starting material, that should be there in the product. So 1, 2, 3. So here 1, 2, 3. This is also carbon that is coming from your reagent. Okay. Why it is called rearrangement? See, I have the same starting material, right? Because starting material, the same starting material I have. When you treat NaOH, so OH minus comes to the picture, right? OH minus comes to the picture. As you know very well, this is a nucleophile. This is a nucleophile, right? And this is a polarized bond, delta minus delta plus. Clearly, this center can act as electrophilic center. So what will happen? It will undergo SN2 reaction. Okay, it will undergo SN2 reaction, and you will end up with this product. What is this? This is alpha hydroxyketone. This is alpha hydroxyketone. Okay, but your product is not alpha hydroxyketone. So clearly this is rearranged product. So you are expecting another different product, that is nothing but this one, right? This is acid. So this is called a rearrangement reaction. This is simply SN2 reaction. So that is the charm of rearrangement. You will end up with an entirely different product what you are expecting from general organic chemistry. That's why it is called a Favorskii rearrangement. So I repeat, the starting material for this reaction is alpha haloketone. When you treat this alpha haloketone with the sodium hydroxide, you will end up with the carboxylic acid. When you treat this with the sodium alkoxide, you will end up with the corresponding ester. The thing is that you just replaced OH by means of OR dash. That is the thing. Okay, the all things are same. Clear? So this is the key point of this reaction. This is the key point of this reaction. So we can discuss what is the mechanism of this reaction. Okay. So you have to know mechanism. Why? Because in examination you should aware about mechanism. Such kind of questions will be there. Okay. So our reaction is this one along with the NaOH. You are expecting this product. Okay. So how will be the mechanism? So I am starting. So our starting material is alpha halobromide, alpha bromo ketone. Okay. So clearly this is called alpha portion, this is also another alpha dash portion. Okay. Now the thing is that you are treating this fellow with NaOH. NaOH furnish OH minus ion, that is a well-known base. The thing is that in this reaction you have two alpha portion. Here also you can see a hydrogen here, alpha hydrogen. Here you can see 3 alpha hydrogen. I am representing only 1 hydrogen. In this reaction, selectively this base abstract this alpha hydrogen. This reaction base halogen opposite hydrogen abstract here. That is very important. Because logically highly acidic hydrogen. Okay. So in general concept, this is highly acidic hydrogen, but in this reaction, this base will abstract this hydrogen. That is the hydrogen which is opposite to the leaving group or halogen. So what will happen? Attack, okay, shift. Okay. So you will end up with a product or intermediate like this carbanion intermediate. Okay, along with the elimination of water molecule. Now what will happen? This is a nucleophilic center, this is an electrophilic center. It will undergo intramolecular SN2 reaction, right? So you will end up with a highly strained 3-membered ring. Okay, ring. Right. This is highly strained 3-membered ring. Now what will happen? In the next step, I am writing the next step below. Okay. In the next step, what will happen? Again, the same reagent comes to the picture, NaOH, that is OH minus ion. It will undergo, this is intramolecular SN2 reaction. Here it will undergo nucleophilic addition to this carbonyl compound. Okay. Now what will happen? You will end up with O minus OH. And this is the crucial step. This is the most important step. What will happen? This lone pair comes back to this position. What will happen? Valency of this carbon will exceed. So it won't happen. So one of these bond will break. Okay. So I'm taking this bond. Okay. So you will get double bond OH. Okay. So you will end up with this carbanion. So be aware that this process is dependent upon stability of of carbanion. You know that stability of carbanion, primary greater than, secondary greater than, tertiary. Now here both are primary, so you can choose any one of the bond. Okay. Finally, what will happen? It will undergo protonation. Okay, it will undergo protonation. You will end up with the desired product. That is, okay, so it will undergo protonation. Okay, here it will undergo protonation. You will end up with the desired product. Okay, so this is the mechanism. Okay, so it's very clear. The thing is that first your base comes and will abstract proton from the opposite side of your halogen, right? You will end up with the carbanion. This carbanion undergo intramolecular SN2 reaction. You will end up with highly strained 3-membered ring. Further, next driving force is that this is highly strained system, so it won't retain. Okay, now again your reagent comes to the picture. It will undergo nucleophilic addition reaction. Now this is highly unstable tetrahedral intermediate, and moreover this is highly strained 3-membered ring, so it need to break. Okay, so it will undergo this kind of cleavage. You will end up with the carbanion and finally your product. The same thing, the same mechanism you can follow. You can choose OR minus when you are using NOR dash. Okay, that is alkoxide ion instead of OH. You will end up with the OR product, that is ester. The same mechanism you can follow. Okay, so I am doing one mechanism only. The same mechanism you can use in if you are using alkoxide, sodium alkoxide as a reagent. So your nucleophile becomes OR minus in that situation. Okay, so you can end up with the product OR dash. Okay, OR dash. Ready? Clear? In Favorskii rearrangement, we can have 3 different type of substrate. Already we have discussed about alpha haloketone. Now you can see alpha dihaloketone. It will undergo Favorskii rearrangement, and alpha dash dihaloketone, it will also undergo Favorskii rearrangement. Where alpha haloketone give you carboxylic acid, right? If you treat with NaOH. But if alpha dash and alpha dash give you alpha beta unsaturated carboxylic acid. Just the thing is that you have a double bond here at the alpha beta position. That is the difference. So these are the 3 different types of substrate that will undergo Favorskii rearrangement, right? So very simple. So we can take one of the either alpha dihaloketone. How will be this product is formed? Let's check the mechanism. Okay. I am taking alpha dihaloketone. Our expected product is this. This is alpha dihaloketone. And this is alpha beta unsaturated. Okay, mechanism. So here you have 2 bromine. When you treat with NaOH, you can see OH minus in the picture, and here you can have hydrogen. We already mentioned proton abstraction takes place the opposite position of halogen or leaving group. So OH minus ion comes to the picture. Okay, that is your base comes to the picture. It will abstract this proton and you will enter with the carbanion. The same mechanism, a little bit difference you can observe. Br, right? So carbanion. Now the same thing happened. Intramolecular SN2 reaction. Okay, attack shaped. This is nothing but SN2 reaction. You will end up with the highly strained 3-membered ring, right? Like this. This is the new bond. Okay. Now one of the Br remain. Okay. Now in the next step, what will happen? The same things what we have learned earlier case. It will undergo nucleophilic addition. Okay, nucleophilic addition. You will end up with this highly strained adage. Okay, OH Br. here the selectivity is that the bond break will happen, or the carbanion will form in such a way that the carbanion formed opposite to the Br. Okay, let's see how it is. Shift, this bond will break. Why? Because carbanion formed this portion, it is opposite to the Br. So break. Okay, so you will end up with a double bond OH, carbanion here and Br here. Why this? If you generate carbanion here, it can move away this Br and you will end up with the alkene. Okay, that is the charm of this reaction. Okay, so you will end up with this double bond. Okay, ready, OH, elimination of Br. The same thing happened in the case of alpha dash dihaloketone. You will end up with the alpha beta unsaturated carboxylic acid. The carbanion formation mainly depend upon the position of a halogen. Okay, so carbanion formed opposite to the halogen remain in the system, so that you can have an alkene by this kind of even CB elimination. That is, this is the conjugate base. Okay, this is called even CB elimination. It is conjugate base of its acid. Okay, and this move and this get eliminated. This is even CB elimination. Clear? Okay, so these are the three different substrate you can see in the case of Favorskii rearrangement. Okay, so I hope you got the concept. Okay, so go through the some example. Okay, thank you.